if last week that our projector is working, that I want to show you guys first. Okay, so this is what I call 1.5 page reaction. And all the reaction looks like this. If you want to have a closed loop, it has a reactant which looks like something like this, and it has a condition and the products. In 118A, you have 17 reactions that's with mechanism on it. I'm going to show you in a second. So that's 1.5 page reaction, a table, which is not the table that I'm going to do today, but it's still important. And a map. So in that reaction map, it's made with the same thing that I told you guys from this piece of paper. But this time we want to put the thing that's basically from the same character, or they have the same functional group together, like alcohol in the middle. So let's see how alcohol reacts with something else. That's what I call reaction map. This is my expectation from you guys for getting a good grade for 118A, or at least I did those stuff to help me study. And another thing that I want to show you guys is later on you are going to meet something called mechanism, which looks like this. I think last week I wrote on this board resonance, reaction, and mechanism. Okay, a mechanism is the blue part. You are drawing arrows, right? I will call it a sentence. A sentence made up of all those arrows, which is the transferring or the moving of electrons. So this is a note of 118B, which you can do the same format if you want for 118A. Once you start to learn reactions and mechanisms, you put half of the page empty, because it's going to annoy you if you have something like the bond angles, and you want to show that, and you have lines just come across with your structure. So half of the page with empty, and half of the page with line. And something good with it is because if you are printing on both sides, you can still see some lines. If you want to draw those reactions in a really good shape, you can, because you can still see the line on the back of the page. That's something I think is really good. But I would say 50-50 is a good percentage to use. I use that for my 118B and 118C. Okay. Another thing that I also mentioned last time, but I didn't get a chance to show you guys, is the notebook. That note is something after you took like whatever, after you learn everything. But during a lecture, this is my notebook for 118 series. What I mentioned last time, that reaction is the first name of a whatever chemistry, and mechanism is the surname of that. So you need to match your first name and surname together. Whenever you come to it, it's the same thing. So that's what I did, like this page. Okay, I like this page. So when my professor told me a reaction, which I numbered with a number 10, and the next one with 11, if he told you the reaction and the mechanism at the same time, good. Then I use the same color for mechanism if it's necessary. But sometimes he just talks through the mechanism, and he said, okay, this mechanism and the mechanism for reaction 11 is really similar to each other. He directly taught us how to do the mechanism of the next one, and he didn't really told us the reaction. In this case, I want you to realize that this is another reaction, although he didn't really write out. I want you to leave some space on your notebook, so later on you can fill in the first name of this reaction. Afterwards, you always need to match your reaction and the mechanism. That's something that I once told you last time, but I didn't get the chance to show you on this projector. Did I make this point clear? Okay, so that's kind of some tips, which I should have shown you last week. Now let's come to today's content. Today what we are going to learn is hybridization and resonance again. So hybridization, resonance, and some Newman projection. As I mentioned before, there are only 3 things that I want you guys to practice as crazy as you can. One is resonance, which means hybridization And the Newman projection is not one of them. For this part, my expectation from you guys is you know how to do it. It's not something like resonance, reaction, and mechanism. Even you know how to do it, you're not going to get them 100% correct. Although you all know how to transfer electrons, you probably don't get correct charge, don't get correct precision of that charge, or anything is possible to happen. But hybridization and Newman projection is something that as long as you know how to do it, that's fine. So don't practice as hard as resonance. I want to save your energy for later on. Okay, let's start. First is bond angles. Bond angles and geometry. I have some model kits. Let's see the first one, which is sp3 hybridization. Usually happen to like alkynes. So it has 4 bonds because carbon has 4 valence bonds and it's tetrahedral. The angle, you just need to remember this number. In the whole 180 series, that's probably only the quiz you are going to write down these numbers. You just need to know. That's the fact. The second one is sp2 with 120 degrees. So that's the angle from here, and here. They are all 120 degrees. So we think this is a bond, and that's 120. Different from the sp3 hybridization, it's in the same plane, so it's a planar geometry. That's something you should keep in mind. Actually, on this carbon, you have p orbitals, which is pointing up. It has something to do with later on, when 180V, you're going to learn something called aromatic, which is how the electrons in p orbitals moving out. It's still resonance. That's why resonance is important. And the sp hybridization is, I don't have the model kit, but it's 180 degrees, which means you have the triple bond in the middle and whatever else pointing on each side. And then we just quickly draw what is the wedge dash structure. Hopefully you know how to do it. So I will draw 2 carbon first. Let me zoom in. Okay, that's the maximum. Okay, I will draw 2 carbon first. And then we are going to see how that's going to be different on each of them. It's something basic and it's not that hard, but I hope you guys can get some useful information from this part. The first one, since it's sp3 hybridization, and you always know the 4 bonds are single bond, so it's going to just spread out like that. It's really similar to the example we do last week. And then double bond is something we just say it's going to be planar, so it's not going to have the wedge dash. That's also something I said last week. We never draw wedge or dash on the carbon in a carbon-carbon double bond because it's plain. And triple bond. Okay. So we use 2 carbon as an example to see what this 1, 2, 3 structure looks like. And then we're going to count on the bonds we have. When we are counting the bonds, it's also the same on your discussion menu, but I hope it states, but probably it didn't really state clearly, is we are only talking about the carbon. It's only one of them. So I just highlight the carbon that I'm talking with. When talking about the first pink carbon in this first structure, which is an alkyne, how many sigma bond we have? Sigma bond in this case just single bond. So when you are counting sigma bond, it's counting the single bond it has. Totally it has 4. You just need to remember. But I want to say it more specifically, which is these 4 sigma bonds include 3 sigma carbon hydrogen bond, which is 1, 2, 3, and then 1 sigma carbon-carbon. So that's how this 4 comes from. And then the same goes to the second structure. How many sigma bonds we have? Let's just count. It's 2 sigma carbon-hydrogen sigma bond and 1 carbon-carbon sigma bond. So carbon has to have 4 bonds. In the first one, which is 4 sigma bond, which means it has 0 pi bond in sp3 hybridization. But in the second structure, we only have 3 sigma bond, which means the last one has to be pi bond. The same thing goes to the third one. Sp hybridization, it has 2 sigma bond, which is 1 sigma carbon-hydrogen bond and 1 sigma carbon-carbon bond. And the rest, okay, this 1 pi bond is the carbon-carbon bond, this 2 pi bond, carbon-carbon bond. You don't need to know how to draw the pi carbon-carbon things. This is something that you just need to know. Why write down pi carbon-carbon? It means the pi bonds between carbon-carbon. You just need to know, in your state, you just need to know how many bonds are there. That's enough. Okay, something that is more useful is example, which means very likely in your worksheets is in your quiz, I can tell you it's not likely it's 100% you're going to assign the hybridization of some structures like the ones below. And then you are going to assign hybridization of each atom in your quiz. That's what kind of question that you're going to be asked in the quiz and also in midterms. So you don't have time to really count the bonds to identify what those things are. What I do usually is just remember, if it's just like a nitron or alkyne, something like this. This nitrogen is sp3 hybridization. This carbon is sp3 hybridization. And something that you are expected to know, but you are not going to lose points on this thing, is oxygen. And in the worksheets that I send out through the email, that's more detail orientated. That one is the worksheet that suits better for instructor, another instructor, which is Levens. She will make problems on oxygen, but Professor Neil is not going to make questions on oxygen, so you don't need to worry about that. But I can tell you, the way that I do this kind of problem is just, I want to see how many double bond it has, or triple bond. If it doesn't have any, it's sp3, no matter what atom it is. That's the way I do it. I think it's a straightforward method to use, and so you are not going to lose point on oxygen in Professor Neil Sean's whatever quiz or midterms, because we are not going to ask you any question on oxygen hybridization. But nitrogen and carbon is possible. Good. And something else, in sp2, that's basically is for double bond. The same thing. For carbonyl, which is CO double bond, we're not going to ask you oxygen. So the maximum that we are going to ask you on this one is ask you that what's the hybridization of the carbon in carbonyl. So don't worry about oxygen. And another reason in this case, in the carbonyl, the CO double bond, we are not going to ask you oxygen. Oxygen is a terminal atom. So that's another thing that you can just be relaxed on, is we are not going to ask you a question on terminal atom, because hybridization is kind of what we use to explain why this shape looks like this. And if everything has something to do with geometry. And if it's like a terminal atom, you cannot draw the whole geometry of the things that we can, like in the middle of the structure. So we are not going to ask you what's the hybridization of anything at the end, like the hydrogen at the end. We are not going to ask you something question like that. And triple bond, it's just triple bond. not going to ask you on nitrogen in this case. So I would say this is a more useful tool that you need to keep in mind. For how many bonds is in this structure, you just need to know it. You just need to know how to do one problem. You're good with the rest. And something that you see resonance structure again, right? That has something to do with, it's going to affect your assigning of hybridization, which we are going to see 2 examples in the below. First, I want you to draw the resonance structure of these 2, like what you did in quiz just now. And we are going to assign hybridization after that. And you will see why. I'm going to do with you, so do it. I'm going to hide my answer. I'm going to do it at the same time. Okay. Yeah. If you finish the first page, you can turn to the back. That's more practice on assigning hybridization. I guarantee you this is something similar to your quiz. But hopefully you still remember to review those contents when you are in week 4. Okay, I didn't put all the arrows and chart on. If you finish it, you just watch me do it for real quick. This is some help if you don't really know how to draw a resonance structure. In this case, I will just do it, which I move the long pair electrons on oxygen into the carbon and oxygen bond and push the double bond onto the oxygen. So it's going to make, so I'm coloring the long pair that's forming. So previously this oxygen have 2 pairs of long hair, and this new pink bond is forming by that. And then also because this oxygen is losing a pair of electrons, you need to have a positive charge. Okay, this is also something I talked about last week, but I see a lot of students still making mistakes in my previous section. So I will just say that again. Always check your charge. When you draw your resonance structure, they forgot to put positive on oxygen because they think oxygen is very electronegative, then it shouldn't have a positive charge. Okay, so whenever you are donating your electrons out, you donate something, electron, right? Electron is negative, then you have to form a positive charge on yourself, although oxygen is very electronegative in this case. That's just the rule to do it. And the same thing for the next one. So oxygen is going to donate its electrons, and then it's going to form something similar to that. Okay, so oxygen still have a pair of long pair, but this time because we are moving, we are moving this pair of electron into the carbon next to it, so it forms a negative charge on carbon. So this is the correct resonance structure for these 2 compounds. Then we are going to use the tools that we just, like the table, how we are going to assign hybridization. Since I will just use, if it has double bond, it's sp2. Look this oxygen. Previously I told you if it's oxygen and it's all single bond, it's sp3. It looks like it's the case, but because it has resonance structure and it can have a resonance structure with double bond on oxygen. So this oxygen is actually sp2 hybridization. Does that make sense? I'm going to repeat this one again. So previously, I just told you if oxygen is in the middle and it's all single bond, it's going to be sp3 hybridization, right? So in this case, it looks like this oxygen is really similar to this case, that it's single bonded to other. But because it has a resonance structure, and in that resonance structure, oxygen is in a double bond format. So we still consider this oxygen to be sp2 hybridization because it has double bond. Makes sense? The same thing happens to the oxygen next to it. Although previously it looks like this oxygen is bonding to something else, it's all single bonded, and I'm using a tool in the table, it's going to be sp3. It looks like it's the case. But because it has a resonance structure with a double bond on it, it's actually sp2.
I have a question.
See that? Yeah.
Couldn't you just move over all the double bonds in the ring and get another resonance structure for the bottom one?
Yes. Okay. So do you want me to draw more resonance structure of this one? Is that what you mean?
Oh, I just wanted to clarify. There are more though, right?
Yes, you can. Because in this case, no matter how you're going to draw on the rest of the ring, which I can just draw one really quick. So let's say I move this long pair into this two carbon, and it's going to push the pi bonds onto this carbon. So this resonance structure should look like this. This is the new forming formal negative charge, and this is the new forming pi bond. And oxygen is not going to make any change in this case. Since everything that's just moving electron in a ring, and it's not going to affect the oxygen. So it's the same if you want to draw more. I mean, you can, if you want, to draw more, which is like this. So I don't care how you draw. I just the things I'm talking about here is about oxygen. But I encourage all of you guys to practice on drawing as many resonance structure as you can in your free time. Yeah.
And you said that because that oxygen, it has a resonance structure in which it's sp2, the original one is sp2, has hybridization of sp2?
No. If it's this one, this oxygen is sp3. It's exactly the same example here.
Okay.
So this one is sp3, but just because, so the reason it's sp3 is, in my case, in my words, is it doesn't have double bond. But because its resonance structure has double bond, and we talk about what resonance structure is basically the picture, two different pictures of the same molecule, which means in some case, it wants to form a double bond to show a more stable structure or whatever reason, then this oxygen is sp2 because it has the format of double bond. Good. And I told you guys we are not going to be asked on question of oxygen. It's the same thing with nitrogen. So, have a practice on the back of the third molecule. That's the one with exactly the same situation. I'll leave the front page so you can have something kind of, is that, yeah, okay. I'll leave this front page here and do the third structure on the back. Nitrogen has the same lone pair that can be moved, nitrogen can donate its lone pair to other things. So you may be asked a question about nitrogen in your quiz. Okay, let me walk you guys through. It's still practice on resonance structure. This nitrogen donates its lone pair into carbon-nitrogen bond, and it's going to kick the carbonyl pi bond onto the oxygen. So this is its resonance structure. I'll copy the rest of the thing here. And then oxygen has a negative charge. Nitrogen is going to have a positive charge. Since it's donating its electrons out. So this is the resonance structure. I will focus on this one. So in this case, this nitrogen is double bonded, so it's sp2. Carbonyl, sp2. Oxygen, since it has a format of double bond, so it's still sp2. Double bond, sp2. Double bond, sp2. The end, single bond, sp3. sp3. So this is something that you are supposing to do on your quiz, which is assigning hybridization of the atoms. And I put the other two structure on the left. I will zoom out a little bit so you can take the footnotes. Okay. The first one, nitrogen, double bonded, sp2. The rest of them is the same. They are all sp2. So I will just write all sp2. In this case, this triple bond, which is cyano group, is sp hybridization because this is triple bond. And this one is sp3. It doesn't have any double bond or triple bond. And this nitrogen is sp3. The rest of them are all sp3. The same for this one, the same for this one. Okay. We are not going to ask you terminal atoms in this case. The nitrogen we are not going to ask you. Any questions on how to assigning hybridization? Good. Newman projection on your discussion menu, you are supposed to know two things. Two compound. One is ethane, which has 2 carbon, and the rest of them is hydrogen. In this case, you can imagine only the 2 black atoms are carbon, and the rest of them are all hydrogen. So that's one thing you can know. One word to say is whenever you are rotated, it wants to be in 60-degree dihedral angle. So this angle is called dihedral angle. We're going to talk about that later. This looks something better than this one, which means whenever you are doing a rotation on a Newman projection, you always want each atoms to be not hide anyone. In this case, you also need to do a Newman projection on butane, which has 4 carbon. So that's why I made a little change. This orange one and this yellow one are 2 methyl groups that we can just differentiate by the color. The blue atoms are hydrogen. So to rotate this atom and to draw what you see. In this case, because we have 2 carbon, and if we are just looking through the carbon bond, one of the carbon you cannot see. The carbon behind is drawn like the circle here. So that's why we use Newman projection to sketch what we see. In this case, the first one has a methyl group pointing up, which is the orange one. I'll use that orange, my orange pen. Okay, so this is the orange group. And then the carbon in behind has purple bond. So in that case, you can see the bonds linking to the first carbon in front has white bond, and it has an orange methyl group. The back one has a yellow methyl group. The yellow one, I will use a green pen. Okay, so this is the yellow one. Okay, and then the rest are just hydrogen. So does it look something similar to what you have seen here on this structure? Somehow similar, right? So we call this structure anti. Anti means your large group, which in this case our 2 methyl group, are in opposite position with each other. after that, we are going to start to rotate. That's why we have a 60, 120, 180 degree here. So the first thing we want to rotate is fix one carbon and then rotate the other one. Otherwise, you are never going to, it's going to take forever. So we're going to fix the front carbon. Since I have already printed out the one in front with the orange one on top, it's not going to move. We just rotate the one on the back. So the front one is still CH3. You can put orange CH3 on all of them. I don't mind you to do that, because we are going to fix that one. And our blue hydrogen on the front, in the front. My bad. I know my English is not my mother language. Okay. So let's come back. After I put my orange methyl group up and I fixed the first one, we're going to start to rotate. The first rotation takes 60 degrees, which is the position we don't like. In this case, imagine this methyl group is actually another black thing, like this. So it starts large. If it's like this, and you have something else here, they're going to knock each other. In reality, they're all nitrogen, and they're all negative. They don't want to be too close to each other, especially in this case. So this is a conformer that we call all of those things conformers. This is a conformer that is not, this molecular is not very happy with. So I'm going to use a name. So first I'm going to draw it. Our methyl group, the yellow one, I will use the green pen. Okay. Our yellow methyl group is fat, and then the rest of them are just hydrogen. And we call this kind of conformer eclipse, Eclipse. Okay. Eclipse conformer. This is a conformer we don't really like, but we can just move on to something we like. This. Okay, in this case, I'm going to fold this one. Otherwise, I'm not going to see what is on the screen. Okay. In this case, my methyl group is pointing up. The other methyl group is just 60 degrees to it, right? This angle is 60 degrees. So that's something we can draw on this Newman projection. So that's another methyl group. Hydrogen, one of the hydrogen is pointing down, and the other hydrogen. We call this conformer gauche. Or if you are French, I believe it should be gauche. But anyway, that's, as long as you know the word, that's fine. Keep moving. My two methyl group are knocking each other. So this is still eclipse. But you can imagine this is the structure that has the highest energy, since it doesn't like this very much. The two methyl group, they're very bulky, and they are really trying to avoid doing this. So imagine we are rotating, then this one probably won't last longer. Then it will very quickly move on to this, which is another gauge conformer. Okay, previous one I didn't really draw it. So previous one, our yellow methyl group is as the back of that, and two hydrogen. Keep moving is our gauge structure again, and in this case, my methyl group moves to the right. Hydrogen. And then keep moving something that you know before is still eclipse. And then you have the methyl group at the corner. Hydrogen, hydrogen. And finally, everything turned back to original, which is anti. Methyl group, hydrogen, anti. So basically, you can see that's the rotation of this yellow methyl group. We fixed the first one, and we sketch what we see on this projection. Always remember, because you can see the front white bond, so the front one you can see. The one that has been hidden is the one that you draw from the circle. So always remember that. And one more thing that you are expected to know. So everyone good with the model kit and the conformance? Good? Okay. So one more thing that you need to know about those things is how comfortable it is, which we just talked about that during the rotation. So we know anti-position is really happy because the bulky groups are in anti-position. They're in opposite directions. So that's something good. Okay, I'm going to use a ruler, but it's fine if you don't. So this is the lowest energy, our starting point. They should be the same. And then is gauge. This is also similar to anti-position, but in this case, our two metal groups, they're closer to each other. So it should have higher energy since it's not as comfortable as anti-position. So our gauge position should have a higher energy than anti. Okay. What else? 1, 2, 3. The 3 conformer left is R, eclipse the conformer. So the most uncomfortable one is the one with 2 metal groups in the same line that you cannot see, which is the one in the middle. This one has the highest energy because it's the most uncomfortable one. And it's here. Later on, the other two, this one is the same here. They are eclipse. They are not happy. But they are the same thing in this case. So we just by how comfortable the conformer is, we know like the energy, and since it's rotation, it should be smoothly changed through those conformers. The same for the energy. And you just link them with smooth line. Okay. So my expectation for you guys for this one is just knowing how to draw. This is the case that I show you guys how to rotate. And in the future, you probably don't really need one because you can just imagine. So we are looking from this angle, which is like this, right? So this is the this carbon. So methyl group is this one, and the 2 carbon. See, it looks really like the shape. So in the future, you just need to know if you are looking through this angle and you do a 90-degree, you are really looking through this point, then it should be something like this. On the worksheet, question number 3, if you go ahead to read the question, it only asks you to draw out anti or gauge conformers, which means you just need to know which one has the lowest energy. The other kind of way to ask the question is, please draw the lowest energy conformer in Newman projection of this molecule below. So that's kind of question we ask. You need to know eclipse the conformer with both bulky group in the same position is the highest energy one, and untimed position is the lowest one. That's good. So kind of you just need to know how to do it, then you can do it. Good. on this part, Newman projection and conformer. No? Okay. Pi bond, in this case, the double bond is where the starting point of our resonance structure. You can do either way, but because this is double bond and this is a positive charge, which means the easiest way to do is from here. It's the same from this end. In this case, I just want to draw the one that I'm happy with, okay? But it's fine if you are happy with the others. Oh, I shouldn't use a green. Okay, that's fine. I will use a green one to label it. So this arrow is green, which means the new forming bond is going to be green. And then my structure is blue. Always check the charge. Since you are donating electrons out, you should form a positive charge on this carbon. And we talked about this last time. This is a carbon cation, right? And then we can keep moving. The way we do it, let me change the color. This is the bond we just formed. We're not going to break that one. We just move the other one to here. And in this case, it's going to be, I still keep my green bonds there. My blue bond, and my orange new forming bond. Since this bond has been donated into this position, then I form a positive charge here. So that's the carbon cation. It's the same. If you want to, let me just draw the same structure here. So I just draw the same thing again. If you want to start from this end, which is, if you want to start here, it's still going to give you the same structure. See? So this is the 3 correct structure. Do not transfer electron out, because this one is sp3 hybridization. Since we talk about hybridization now, another small tip that you can keep in mind is when you are transferring, this one, since it's positive charge, it has a MPP orbitals. In this case, then it can accept electrons. sp3, it already 4 bonds are bonded to that carbon. It doesn't have empty orbitals to accept lone pair from others. So it's wrong if you want to draw the thing out. Then someone is going to ask me, how about benzene? I see what you did last time, which is transferring like this, like this, like this. The reason I can do this on benzene is because all of the carbon is sp2 hybridization, which means they all have the MPP. Yeah, question?
So I think for this question, we have 5 resonance structure in total. So when you get this third one, you can actually move the double bond to the carbon cation one, and the carbon cation just move to the upper left.
Oh, you mean you want to keep moving like this?
Yeah.
Oh, yeah, sure.
So in total, we have 5 structures.
Oh, okay, good. So in this case, that's something good. So you mean this one, and a positive charge here, right?
Yes.
So, yeah, any possible ones that is within the ring, and you are following the rules that I just told you, you're good. But the things that I will mark wrong is if you transfer the bond to the outside. That's something wrong. Good? Okay. Okay. Since it's 2 point each, as long as you have 2 correct structures, I will give you full marks, but I will let you know if you did something wrong. Good. Previous naming stuff, I think that's the 3 questions. I will just, like this one. How many people have questions on the first 3? Is that very hard, or I can just post the answer later on, then we can come back to the conformer? Okay. Basically, I only want to talk about the resonance structure. How about you do this one again? The ones that just shown. I don't know if that's because of the question. I see people did poor job on this one, resonance structure, which I feel like it shouldn't be like that. this one, first, the one who designed this quiz is not my format. You can tell from the format that I didn't make this quiz, because if I'm making the quiz, I definitely will draw the long hair on oxygen. And then the most common question I see is they do know how to transfer the oxygen, long hair on oxygen to the carbon oxygen bond, but they are start use pencil. They are start to move on like this. And then they say, I have a double bond here, and I'm going to push this double bond to here. And then they're wrong. The reason that you can do this is correct, but you cannot push electron anymore is because this carbon is sp3 hybridization, and it cannot accept any more electrons. So the correct way to do this one, even though you are not doing this quiz, but you might meet something similar like that, is first you can push the electron at the corner. Stop. I will do one arrow each. If I'm gaining points from drawing a correct resonance structure, the left arrow I'm drawing, the less chance I'm going to get the thing wrong. So I will just draw the first one like this. And then it's oxygen. And then this has to be a negative charge. And losing that negative charge is another common mistake I see, which I just told you guys now. Pay attention to that. Oh, I lose a double bond. And then if we keep moving the electrons to here, since I told you it's wrong to do it here on sp3 hybridization, it's fine if you just put it on the corner. So it's going to be something like this. Oxygen and my new forming double bond like this. So in this case, because the rest of them are sp3, you cannot move electron anymore. The only choice is move electron back, which is going to give you the previous structure. So in this case, it only has 3. It only has these 3 structures. Good. Any questions on this one? Okay. We're going to finish here and try to do the questions on your worksheet too. And then hopefully in week 4 when I see you, you still know my name and my section. Okay.